Okay, this is the last video of the AS level 9.2, constant acceleration formulae, constant acceleration. So we're talking about SUVAT again. You can use calculus to come by the formula for motion with constant acceleration. Now, if you remember rightly, we did that graph of velocity against time, and we said the change in velocity, and we talked about all of this, and we got all of our SUVAT equations from looking at this graph and the area underneath it. There is another way of deriving or coming by the formula just using calculus, and this is how we do it. So particle moves in a straight line with constant acceleration, a meters per second squared. So that means a isn't variable, a is a constant, it's a fixed number, it doesn't vary. Given that its initial velocity is u meters per second and its initial displacement is 0 meters, prove that a, its velocity, is given by that. Well, if we're going to use calculus here, then what I know is that the acceleration is constant. So I can write down the opening statement, which is acceleration, which can be written as dv by dt, and we know that that is equal to acceleration. And I'll say it again, that isn't a variable, that is a constant. Now, if I integrate both sides of this with respect to t, what I end up with is integrating that with respect to t and integrating that with respect to t. If you integrate that with respect to t, you end up with v. Integrate that with respect to t, bear in mind that is not a variable, it is just going to be a t plus a constant of integration. Now we know some opening boundary conditions, that the velocity is equal to u when the time is equal to 0. So the initial velocity is when the time begins. So shoving that into there, you end up with u is equal to, that's disappeared, c. So therefore we end up with the well-known formula that v equals u plus at. Okay, and that's how you derive it using calculus, by starting with the opening gambit, which is the dv by dt is equal to acceleration. Okay, right, in a similar vein, it says you've got to derive its displacement s meters at time t when to show that s equals ut plus a half at squared. If I squeeze that in here, we start with this. So if you're ever asked in an exam to do that, you can't assume this. You have to do this bit first, get to there, and then from that bit there, you're then going to say that v is equal to ds by dt. Okay, so therefore you will end up with ds by dt is equal to u plus at. And again, you're going to integrate both sides with respect to t. Okay, with respect to t. So all of that is going to be integrated with respect to t. So you're going to end up with integrating this with respect to t gives you s is equal to, that becomes ut, and that becomes ut squared divided by the new power is 2, so it is a half at squared. Okay, and then you got plus c. Well, we know that this constant of integration, we know that the displacement is 0 when it was first observed at t equals 0. So therefore you can quite clearly see that's 0, 0, 0. C is therefore 0. Okay, so finally, therefore you end up with the equation that we know, s equals ut plus a half at squared. Okay, and as I said, if you're asked to derive this one in an exam, you have to go through this procedure, then hit this procedure. You can't just hit the ground running assuming that. Right, over the page. Okay, we've got the exercises, the final exercise, and I'll also attach with the notes the mixed exercises. Okay, any problems, you must email me and I'll go over the question. Okay, good luck.